What if a story, written in an alphabet of ice and dust, traveled for longer than our Earth has existed, just to whisper its secrets into our telescopes for a few fleeting months? Imagine a messenger from a star system that may have died billions of years ago, a silent wanderer carrying the chemical fingerprint of a world we will never see. This isn't science fiction. This is the story of 3I Atlas, an object that didn't just pass through our solar system in 2025. It passed through our understanding of the universe itself, forcing us to confront the sheer scale of time, the diversity of creation, and the profound, beautiful loneliness of our own existence. It arrived as a ghost from a lost sun, and what it showed us changes everything. So, find a quiet moment, settle in, because this journey takes us to the edge of space, time, and comprehension. On the first day of July in the year 2025, the world was, for the most part, completely unaware that it was about to receive a visitor of almost unimaginable antiquity. In the arid, high-altitude desert of Chile, under skies so clear they seem like polished obsidian, the ATLAS, Asteroid Terrestrial Impact Last Alert System, telescope at Rio Hurtado, was doing what it does every night: scanning the heavens. It isn't looking for grand nebulae or distant galaxies. Its job is more urgent, more pragmatic. It's a sentinel, designed to spot rocks moving in the dark, potential threats to our planet. It sifts through terabytes of data, its algorithms trained to notice one thing above all else: movement. And on that night, the algorithm flagged a dot. It was faint, just a whisper of light against the ridiculously dense star field of the Sagittarius constellation. To the naked eye, this region of the sky is a luminous river, the glowing heart of our own Milky Way galaxy. For a telescope, it's a nightmare. Trying to spot a single moving object there is, as one astronomer described it, like trying to find a specific needle moving through a field of billions of other needles. But the software, devoid of poetic distraction, saw it. A single point of light, magnitude 18, so dim that most amateur astronomers with backyard telescopes would have no hope of ever resolving it. Crucially, this dot was not where it was supposed to be. It was moving, and it was moving fast. The initial calculation was almost certainly a mistake. 221,000 kilometers per hour. That's nearly 61 kilometers every single second. To put that into perspective, if you could travel at that speed, you could circumnavigate the entire Earth at the equator in just over 11 minutes. It's a speed that defies solar mechanics. Nothing that belongs to our Sun, not from the asteroid belt between Mars and Jupiter, not from the frozen graveyard of the Kuiper belt beyond Neptune, and not even from the theoretical ghostly shell of the Oort cloud, a light year away, should be moving that fast on that trajectory. Objects that orbit our Sun follow predictable elliptical paths, cosmic racetracks dictated by gravity. They are tethered. This thing was not. Within hours, as observatories across the planet were alerted and turned their own eyes toward the anomaly, the confirmation came flooding in. The trajectory was not an ellipse. It was a perfect, unambiguous hyperbola. This is a word we use, but its meaning in this context is profound. A hyperbolic trajectory is the geometric signature of an escapee. It is the path of an object with so much energy, so much momentum, that our Sun's immense gravity is nothing more than a temporary inconvenience. It can bend its path, like a stone skipping off the surface of a pond, but it can never capture it. This object was not from here. It was passing through, a tourist on a journey that began long before our solar system was even a glimmer in the cosmos, and this would be its one and only visit. It was given a name: 3I Atlas. The 3I is a designation that carries immense weight. It stands for the third interstellar object we have ever confirmed. The first, 1I Oumuamua in 2017, was a bizarre cigar-shaped enigma that tumbled past us, leaving more questions than answers. The second, 2I Borisov in 2019, was more familiar. It looked and acted like a comet, the first definitive proof that other stars produce objects just like our own. But 3I Atlas was different. It was the next chapter, and it promised to be a saga. The discovery triggered a frantic digital archaeology. Astronomers around the world began to dig. They sifted through petabytes of archived data from other sky surveys, looking for pre-discovery images. They were asking a simple question: when did it first cross our threshold? Had we seen it before, and simply not noticed? Sam Dean, an amateur astronomer with a professional's dedication, was among the first to trace its path backward. He found it lurking in server data from June 5th to June 29th, 34 days of images where this cosmic ghost had been hiding in plain sight, its subtle movement lost in the glare of the galactic center. The Zwicky Transient Facility at Palomar Observatory pushed the timeline back even further, finding the earliest confirmed sighting on June 14th. This earliest image was perhaps the most revealing. At that moment, 3I Atlas was 4.51 astronomical units from the Sun, and AU is the distance from the Earth to the Sun, about 150 million kilometers. That's deep space, far beyond the orbit of Mars. At that distance, our Sun is a brilliant but remote star, and the cold is absolute. Water ice, the engine that drives most comets in our solar system, is frozen solid, inert. Yet even out there, 3I Atlas was already active. It was already glowing. It was already releasing gas into the void. This was the first clue that it was playing by a different set of rules. Within 48 hours of its official discovery, the evidence became irrefutable. The Deep Ecliptic Survey in Chile, the Lowell Discovery Telescope in Arizona, the Canada-France-Hawaii Telescope on the sacred summit of Mauna Kea, all saw the same thing. The faint dot of light was not perfectly sharp. It was surrounded by a marginal halo, a faint, fuzzy glow. It had a coma. This wasn't an asteroid, a dead piece of rock. This was a comet, an active, breathing object from another star. The discovery was formalized. The Minor Planet Center, the official record-keeper of the solar system, announced it to the world with two designations: 3I Atlas for its interstellar origin, and C 2025 N1 Atlas, signifying it as a non-periodic comet. The message was clear: say hello and say goodbye. It's never coming back. This process of discovery, from a single anomalous pixel to a global astronomical event, reflects a powerful lesson for our own lives. How often do we move through our days, surrounded by a universe of data, and miss the signs of something profound? We have our own galactic centers, the noisy, distracting parts of our lives that command our attention. Yet sometimes, in the background, a faint signal is trying to get through. It could be a subtle shift in a relationship, a nagging feeling about our career path, or a quiet opportunity we fail to notice. The story of 3I Atlas is a testament to the power of paying attention, of using our tools not just to look, but to see. It's about having systems in place, like the Atlas telescope, to flag the anomalies, the things that don't fit the pattern. When your intuition flags something, when a faint dot appears where it shouldn't, do you dismiss it as noise? Or do you, like the astronomers of the world, turn all your attention toward it, knowing it might be the discovery of a lifetime? The moment 3I Atlas was confirmed as a comet, the first and most pressing question was, how big is it? In astronomy, the simplest way to estimate the size of a distant object is to measure its brightness. More light usually means a bigger object. The initial calculations based on its glow were staggering. They suggested a nucleus, the solid central body of the comet, with a diameter of 10 to 20 kilometers. To a layperson, that might not sound like much, but in the context of interstellar visitors, it was a universe-shattering anomaly. It would make 3I Atlas 1,000 times more massive than 2I Borisov. It would be a veritable mountain range, a small world of ice and rock hurtling through our system. And that was the problem. The math didn't work. The logic of discovery dictates that you find the common, small things first. You should find thousands of pebbles before you find a single boulder. Based on the known population of objects in our own galaxy, we should have detected tens of thousands of smaller, Oumuamua-sized interstellar objects before ever stumbling upon a giant like this. Yet we had only found two others. It was a statistical impossibility. It was like walking into a forest for the first time and having your first sighting of an animal be a blue whale. Something was wrong. The brightness was real, but its source was a profound mystery. The cavalry arrived on July 21, 2025. The Hubble Space Telescope, the venerable eye in the sky, turned its mirror toward the visitor. At a distance of 446 million kilometers from Earth, Hubble stared, its instruments tracking the comet's precise hyperbolic path, causing the background stars to streak across the frame like rain on a window pane. The image that came back was both beautiful and confounding. It didn't show a sharp nucleus. Instead, it revealed a teardrop-shaped cocoon of dust, a compact glow about 4,000 kilometers across, extending modestly toward the sun. The nucleus itself, the solid core, was completely invisible, too small to be resolved even by Hubble's legendary vision. But Hubble's observation did something crucial. It put constraints on the mystery. By measuring the brightness profile of the coma, astronomers could calculate an upper limit for the nucleus's size. The result, 5.6 kilometers in diameter. The lower limit, based on how much mass it needed to produce the observed gas, was 440 meters. The most likely size was somewhere under 1 kilometer. This was a relief. It was a size similar to 2I Borisov, a size that fit within our statistical models. But it created an even deeper paradox. If the nucleus was that small, where was all that light coming from? A tiny kilometer-wide block of ice couldn't possibly be glowing that brightly. The next clue came from an observatory designed to see the invisible. The Spherex Space Observatory, which observes in near-infrared wavelengths, stared at 3I Atlas from August 8th to 12th. It wasn't looking for visible light. It was hunting for the chemical signatures of specific molecules. It was looking for the spectral lines of water, carbon dioxide, and carbon monoxide, the primary ices that make up a comet. The results were stunning. Water, the lifeblood of nearly every comet in our solar system, was undetected. Carbon monoxide was also absent. But carbon dioxide was, in the words of one scientist, blazing. Spherex mapped a vast, symmetric cloud of carbon dioxide gas extending at least 348,000 kilometers from the nucleus. That is nearly the distance from the Earth to the Moon. The comet was shedding 70 kilograms of carbon dioxide every single second. This changed everything. In our solar system, comets are dirty snowballs, mostly water ice. Their activity, their beautiful comas and tails, are driven by the sun's heat turning that water ice directly into gas, sublimation. This process happens efficiently around the orbit of Mars, inside a boundary known as the ice line. But 3I Atlas was observed far beyond that line, where the sun is too weak to sublimate water. Carbon dioxide, however, is a much more volatile ice. It turns to gas at far colder temperatures. 3I Atlas wasn't a dirty snowball. It was a dirty, dry ice ball. This explained its activity so far from the sun. It also began to solve the brightness problem. The intense glow wasn't coming from a giant nucleus, but from this immense, sun-reflecting cloud of carbon dioxide gas and the dust it was carrying with it. Even so, the size question wasn't fully settled. The Spherex data still implied a nucleus of around 5 kilometers if you assumed most of the brightness came from icy fragments in the coma, but could be as large as 46 kilometers if the nucleus itself was responsible for more of the glow. Avi Loeb at Harvard, a scientist known for his provocative theories, calculated the implications of the larger estimate. A 46-kilometer nucleus would have a mass of 33 quadrillion kilograms. This is a number so large it's meaningless, but it's roughly the mass of a small mountain range. It brought back the statistical anomaly. Finding an object this massive should be exceptionally rare. The James Webb Space Telescope, Hubble's powerful successor, delivered the final, crucial pieces of the puzzle on August 6. Its NIR-SPEC instrument, a near-infrared spectrograph of incredible sensitivity, dissected the comet's light. It confirmed the carbon dioxide-dominated coma, saw weak but present water vapor, and even detected trace amounts of carbonyl sulfide. Most importantly, it quantified the ratio of carbon dioxide to water. The mixing ratio was 7.6 to 1. This is among the highest ever observed in any comet, a massive statistical outlier compared to solar system comets. What could this mean? Two primary theories emerged. The first is a story of incredible violence and endurance. If 3I Atlas has been drifting through interstellar space for billions of years, it has been constantly bombarded by high-energy cosmic rays. This cosmic radiation would act like a relentless sandblaster, altering the chemistry of its surface ices, breaking down water molecules, and concentrating more resilient compounds like carbon dioxide. It's a process of aging and weathering on a cosmic scale. The second theory points to its birthplace. Perhaps 3I Atlas formed in a protoplanetary disk around its home star that was simply different from ours. It may have formed very close to that system's carbon dioxide ice line, the region where CO2 freezes, creating a body naturally rich in that compound. It's a classic nature versus nurture debate, written in the language of ice. Was the comet born this way, or was it made this way by its journey? This entire scientific detective story is a powerful metaphor for how we should approach the anomalies in our own lives. We all have a standard model for how our world works, our beliefs, our assumptions, our expectations. But life frequently presents us with anomalous data, events or outcomes that don't fit our model. A project at work fails when it should have succeeded. A person acts in a way that seems completely out of character. Our first instinct is often to reject the data, to assume it's a mistake, just as astronomers first thought the comet's size was a statistical impossibility. But true understanding comes when we do what the scientific community did. We bring in better tools, like Hubble and Webb, to get a clearer picture. We question our initial assumptions. Is the brightness from the nucleus or the coma? We consider all possibilities, even those that challenge our core beliefs. Was it born different, or did its journey change it? The lesson of 3I Atlas is that anomalies are not errors, they are invitations. They are the universe's way of telling us that our map is not the territory, that there is more to reality than our current model can explain. How will you respond the next time life presents you with a blazing cloud of carbon dioxide when you were expecting simple water ice? 1 week before the world knew of 3I Atlas, a young astronomer at Oxford named Matthew Hopkins was defending his doctoral thesis. His life's work, a complex model called the Oort-Oxford model, was an attempt to predict the properties of interstellar objects based on galactic populations. It was theoretical, abstract work. Then, on July 1st, his phone exploded with messages from colleagues. The core of the messages was simple: 3I. His abstract model had just collided with concrete reality, and his model had something extraordinary to say about this new visitor. It predicted that any interstellar object originating from the Milky Way's thick disk should be ancient, somewhere between 7.6 and 14 billion years old. To understand the significance of this, you need a quick lesson in galactic architecture. Our Milky Way galaxy is not a uniform blob. It has structures. Most of the stars we see, including our own Sun, belong to the thin disk, a relatively flat, dense plane of stars that are younger and richer in heavy elements, what astronomers call metals. But surrounding this is a puffier, more diffuse halo of stars called the thick disk. These are the galaxy's old-timers. They are ancient stars, formed in an earlier, more chaotic epoch of the universe, and they are typically lower in metals. They are relics of a bygone era. The trajectory of 3I Atlas was the key. When astronomers broke down its hyperbolic excess velocity, the speed it will have left over after it escapes our Sun's gravity, into galactic coordinates, they found a telling signature. Its W component, the velocity moving perpendicular to the galactic plane, was a blistering 18.55 km/s. It was moving upward, through the galaxy's disk at a speed most nearby stars can't match. This high vertical velocity is a hallmark of the thick disk population. It was like meeting a stranger in a bustling city who speaks a rare, ancient dialect. Their origin is immediately clear. Independent analyses confirmed it. This thing was old. There was a 2/3 chance, as one astronomer put it, that this comet was older than our entire solar system. Let that sink in for a moment. Our Sun and its family of planets, including Earth, formed 4.6 billion years ago. 3I Atlas may have formed 7, 8, maybe even 10 billion years ago. It may predate everything we have ever known or touched. When this comet was a small, icy body coalescing in the disk of another star, our Sun did not exist. It was still just a diffuse cloud of gas and dust, decades or centuries of cosmic time away from ignition. This comet is a fossil, not of life, but of star formation itself, from a time when the chemistry of the galaxy was different. It is a direct, physical link to a past so remote it verges on the mythological. Its journey since then has been one of epic solitude. A study in September 2025 found that 3I Atlas may have passed within about 3 light-years of 25 known stars in just the last 10 million years. This sounds close, but it's still an immense distance. Each of these encounters, however, would have been a gentle gravitational nudge, slightly altering its trajectory, perhaps adding or subtracting a tiny amount of velocity through a gravitational slingshot effect. Now, extrapolate that over billions of years. Billions of years of wandering through the dark, nudged by countless stars, its path braided into an impossibly complex knot. This is why we can never trace it back to a parent star. Its birth certificate is lost to time. It has been wandering for too long. This perspective is both humbling and deeply personal. We, too, are the products of an unimaginably long journey. We don't mean the journey of our own lives, but the journey of the very atoms that make us up. The carbon in our cells, the calcium in our bones, the iron in our blood. These elements were not created at the beginning of the universe. They were forged in the hearts of stars that lived and died billions of years ago. Stars that may have been part of that same ancient thick disk population as the parent star of 3I Atlas. These stellar ashes were scattered across the galaxy, eventually coalescing into the cloud that would form our Sun, our planet, and ultimately, us. Like the comet, we cannot trace our atomic lineage back to a specific parent star. Our physical origins are lost in the mists of cosmic history. But the evidence of that journey is written within us, in our very chemistry. We are, in the most literal sense, stardust. The story of 3I Atlas is our own origin story, writ large across the heavens. It is a reminder that we are connected to a past far deeper and more ancient than we can comprehend. Think about the gravitational nudges in your own life, the chance encounters, the unexpected opportunities, the random setbacks. Each one has subtly altered your trajectory, making you who you are today. You can't trace your current position back to a single starting point because your path is the sum of a billion tiny interactions. The lesson from this ancient wanderer is to embrace this complexity. Your past is not a straight line. It's a beautiful, untraceable web of influences. And just as the comet carries the chemical secrets of its ancient origin, You carry the memories, lessons, and strengths of your own long journey. What ancient star forged the best parts of you? What long-forgotten encounter set you on the path you walk today? To contemplate the journey of Three-Eye Atlas is to contemplate the very nature of our own existence, a brief, complex, and beautiful flicker in the grand ancient story of the cosmos. As the autumn of 2025 deepened, Three-Eye Atlas plunged into the inner solar system. Its perihelion, its closest approach to the Sun, was set for late October. But a cosmic inconvenience stood in the way of our observations. From Earth's perspective, the comet was about to disappear behind the Sun. For weeks, during its most active and interesting phase, it would be lost in the solar glare. It seemed we would miss the main event. But we had an outpost. We had eyes in a different part of the sky. We had robots orbiting Mars. The date was October 3, 2025. On this day, Three-Eye Atlas would make its closest approach to the red planet, passing at a distance of just 30 million kilometers. In human terms, that's an enormous distance, but in cosmic terms, it was a front-row seat. It would be the closest any human-built instrument would get to this interstellar traveler. The opportunity was too precious to ignore. At the European Space Agency, ESA, a decision was made to do something extraordinary: to repurpose spacecraft designed for planetary science into impromptu comet chasers. The primary instrument was the Color and Stereo Surface Imaging System, CASIS camera, aboard the ExoMars Trace Gas Orbiter. This is a machine exquisitely designed to photograph the Martian surface from a few hundred kilometers up. Its purpose is geology. It is not, by any stretch of the imagination, an astronomical telescope designed to image faint, distant targets. Nick Thomas, the principal investigator, admitted how challenging it was. The comet, he stated, was somewhere between 10,000 and 100,000 times fainter than CASIS's usual targets. It was like asking a microscope to take a picture of the moon. The engineers and scientists worked feverishly. They programmed the spacecraft to perform a complex maneuver, tracking the comet's precise motion against the background stars. They took a series of 5-second exposures, the longest they dared, and stacked them together, hoping to build up enough signal to see something, anything. The camera's resolution at that distance translated to about 340 kilometers per pixel. Even the most generous 46-kilometer estimate for the nucleus meant it would be a fraction of a single pixel, completely unresolvable. They weren't hoping to see the comet. They were hoping to see its glow. On October 7th, the images came back across the void. ESA released an animation. And there it was. A slightly fuzzy white dot, moving with purpose near the center of the frame. The background stars were streaked into long lines, proof that the spacecraft had successfully tracked the comet. That fuzzy dot was the coma, the cloud of gas and dust a few thousand kilometers across. It was not a detailed portrait, but it was a profound victory of ingenuity and adaptation. A machine built to study red rocks had captured a traveler from another star. The brightness profile showed a central glow about 680 kilometers wide, clearly extended compared to the sharp points of background stars. It was real. This moment is a powerful lesson in making the most of what you have. So often in our lives, we believe we need the perfect tool, the perfect circumstance, the perfect plan to achieve something. We wait for a dedicated mission to be designed and launched. But opportunity, like Three-Eye Atlas, moves fast. It follows its own trajectory, and it doesn't wait for us to be perfectly prepared. The ESA team didn't have the perfect tool. They had a good enough tool and the creativity to use it in a way its designers never envisioned. They improvised, they adapted, they captured what they could from a fleeting opportunity. How many times do we face an unexpected challenge or chance in our own lives and say, "I'm not equipped for this"? The lesson from the Mars orbiters is to re-examine the tools you already possess. Your skills, your experiences, your network, can they be repurposed? Can you, like the ExoMars team, Point your camera in a new direction and try to capture something extraordinary? The resulting image may not be perfect. It might be a fuzzy dot, but it will be infinitely more valuable than the perfect image you never took because you were waiting for the perfect camera. The success was not in the resolution of the image, but in the audacity of the attempt. The observations from Mars also confirmed something vital. The comet was stable. The consistent brightness and coma structure across the 3 months, from Hubble in July to Cass's in October, showed a steady, continuous outgassing. Many comets, especially first-time visitors to the inner solar system, fragment or have violent outbursts as the sun's heat stresses their fragile structure. 3I Atlas was holding itself together, suggesting a robust nucleus, or a composition that resisted thermal shock. It was an ancient, stoic traveler, not easily perturbed by its brief brush with a star. Data is still being analyzed. Spectrometers on the Mars orbiters also attempted measurements, and if they were successful, they could reveal the isotopic ratios in the comet's gas. These ratios are like a planetary fingerprint. Finding isotopes of carbon or oxygen in different proportions than our own solar system would be the final, irrefutable proof of its alien origin. It would be like analyzing a single drop of water and being able to tell which ocean it came from. As we wait for these results, we are left with the image of that fuzzy dot, a testament to a moment when humanity from its lonely outpost on Mars reached out and touched a ghost from a time before our own. As of now, in late 2025, 3I Atlas is speeding away, having rounded the Sun. It is heading for the outer darkness, past the orbit of Jupiter, never to return. Its brief passage has left a wake of data that will be studied for decades, but more than that, it has left us with a profound sense of perspective. What are the final lessons we can draw from this massive ancient wanderer? First, it teaches us that the universe is not a static backdrop to our lives. It is a dynamic, interconnected system. We are not isolated. Pieces of other star systems can and do visit us, carrying information across unimaginable distances. This should instill in us a sense of both wonder and humility. We are part of something so much larger than our daily concerns. When you feel overwhelmed by a problem, try this. Picture a 33 quadrillion kilogram mountain of ancient ice that has been traveling for 7 billion years, and remember that your life is a brief, brilliant flash in the context of that journey. It doesn't make your problems insignificant, but it can frame them in a way that makes them more manageable. Second, the story of 3I Atlas is a masterclass in confronting the unknown. It defied our models, presented us with paradoxes, and forced us to question our assumptions. This is how knowledge grows. In our own lives, we should learn to embrace anomalies rather than fear them. When something doesn't make sense, get curious. Ask better questions. Bring in new tools and perspectives. The most exciting discoveries, in science and in life, are found not in the confirmation of what we already know, but in the exploration of what we don't understand. Finally, the comet's journey is a metaphor for our own. It is ancient, its path is complex and untraceable, and it was shaped by countless interactions over an immense timescale. So are we. We carry within us the legacy of our ancestors, the lessons of our experiences, and the atoms of long-dead stars. We are, each of us, a unique message in a bottle, traveling on our own hyperbolic trajectory through time. The comet's brief, brilliant apparition in our sky reminds us to make the most of our own fleeting passage, to observe, to learn, to adapt, and to marvel at the sheer, improbable wonder of being here to see it at all. I want to leave you with a question to ponder. If you are a traveler on a long journey, just like 3I Atlas, what is the core composition you are made of? Is it resilient and stable, like the comet's nucleus? And what light, what unique coma of influence and energy are you emitting into the universe around you? Thank you for joining me on this incredible journey to the edge of our solar system and back through the depths of time. I hope this story has given you a new sense of perspective and wonder. Please take care of yourselves and those you love. May your own journey be filled with discovery and light. If you found value in this exploration and want to support our work in bringing these cosmic stories to life, the best way to do so is to subscribe to the channel. We have so much more of the universe to explore together.